Thank you very much, Mr. Chairman.
Yeah, I don't see the presentation, which should come up soon. Before I start talking, sorry for screwing up the program. I hope I didn't too much actually, but I was scheduled to talk before the break. So I come from an island in the middle of the Mediterranean Sea, as you know. Then it is not so easy to go back. So that's the reason why I've been asking to, anticipate my talk. So if the it is on the pen drive. So my talk is on the pen drive. So if we could anyway, let me start saying that as the chairman did, let me bring the greetings from the Sardinia Aerospace District to everybody. It is really a pleasure to be here. Of course, I'm representing at this point my own university, my own institution, but I would like also to emphasize the activity we have been performing as a space district. So if we could have the presentation on the screen, then we could start. Let me anticipate to you that I'll be talking about materials. Particularly, I'll be talking about a specific class of materials, which hopefully will be very useful for hypersonic flights. And the class of material I'll be talking about is relating to ultra high temperature ceramics. So if we could have the presentation, then is Hypersonic is the first one on the pen drive. Sorry for this little.
No,
shall I come over?
No, there is a simple mistake with Bill Gates. Professor Gates, I need your stick, this USB.
No, pen drive is over there. Pen drive is there already, yes. So I gave it to the console when I came. So it is there. We just tried before we started. Sorry for this.
Some kind of competition going on.
Okay, here we are. All right, thanks. So then, as I anticipated earlier, I'll be talking about this class of advanced materials, and I also talk about the characterization we have been performing so far. This talk, as I said earlier, is a joint talk between my own institution, the University of Cagliari, and the institution of Perugia, University of Perugia, where a couple of friends are working there, and they are involved and will be involved in a couple of projects that are very much related to this topic. So, as I said, UHTC, this is a spectrum of the various possible phases that you will see. So basically, you see very hard materials, and of course they will be combined together, as you will see next. But these are the basic characteristics of these materials represented in this slide. So when you want to produce such materials, well, you could go following standard procedures. So basically, you just start from powders, available powders on the market. Then, of course, you just use furnace solution method. What you get typically is powders with low sintering ability. This is a problem. And when you go and take a look at the consolidation methods, then typically what you have is like long processing time. I'm talking about hours, 24 hours, sometimes days. And then at the very end, the product that you get are not the one that you would like to get. So there are issues related to the sinterability of the powders and the length of the processing, of the sintering process of this powder. If you want to produce such materials, which are really very much interesting in this kind of environment, and the reason being that, as you will see later on, they are capable of sustaining really very high temperature under oxidation conditions. So what are the solutions that have been identified so far? There are, routes to use sintering additives. But as you know, when you use sintering additives, then the problem is that you put in your own mixture something that may be dangerous. So that is not all the time the right way to go. Another way to go is to develop powders with high sinterability. This is in fact what we have been doing. And the last advantage is, instead of using standard sintering technologies, use different and more efficient powder consolidation methods. So how do we produce powders? This is a technology that was born in Russia by early 70s. I brought in Italy for the first time when I was very young. I was a PhD student at that time. It was 1988. So I brought it in Italy for the first time, and we started working on this. That's a very efficient technology that is described on the map, is known, well known. So the main point is that you just ignite the sample you want to obtain, and then you get a separating reaction going on through the mixture. And what is interesting is that you really get very high temperature during the propagation of this sample. And this is in fact one of the most important issues that gives you the possibility to obtain powders to be sintered with very interesting characteristics. As far as the powders are concerned, then once you get them, you should go to a more advanced sintering technology, which is the spark plasma sintering one. And basically what you have is actually a powder mixture, whatever you want to consolidate, which is inside a graphite dye. And basically what is interesting here is that the current that is passing through these electrodes does pass through the sample, but it does pass also through the dye. So basically at the end you get the final product in a very short time as compared to the standard technology. I'm talking about 24 hours versus 20 minutes. This is actually the average difference in time to produce the materials you like. This apparatus you are seeing in the picture is the very first one that arrived in Italy back in 2003, and this is available at our institution, Università of Cagliari. This is a Japanese machine, and you could by your own see the characteristic of the machine. What is interesting is that what is occurring as the current passes through the sample. This is in fact a picture as the current passes and as the reaction proceeds inside the sample. So the other interesting aspect is that in Sardinia, in the middle of the Mediterranean Sea, very close to Cagliari, there is a concentration of SPS apparatus. In fact, there are 2 SPS apparatus. I can tell you that in Italy, at this point, there are no more than 5 apparatus altogether. 2 of them are in Sardinia. This is the one that has been obtained. This is a German apparatus from FCT. This has been obtained by this company. It was a spin-off company at a certain time of the University of Cagliari. And this company, through this machine, has been able to produce a nozzle of this type. I'm not going to talk about this result during this presentation, but I want to emphasize such a result. This is a nozzle that is under testing for application for launchers, the Vega launcher particularly. So I would like to show you a couple of systems that we have been able to synthesize so far. So first one is this 3-component system, zircon lebolide, zircon carbide, silicon carbide. This is a relatively old paper we have been publishing so far. So basically you go, as we said, SHS plus SPS. This is actually the strategy, the production strategy. So basically you go and you obtain from the elemental powders the composition you like, and you get the complete conversion under SHS. Then you go and consolidate the powder by SPS, fully dense product. So what is interesting here is that if you just sinter under the same condition the powders available on the market, you do not get the same density. So the powders that are being produced by SHS do display a much higher sinterability. It is clear later, it will be clear later on the reason why. Another system is this afternoon diboride, afternoon disilicide. So in this case, the idea was to show that having demonstrated that SHS is able to give you a very high sinterability of powders, then the question was, okay, let's see if we compare SHS while producing in a single step the design material, or if we just produce by SHS the 2 materials and then combine them. So basically, of course, using these 2 approaches, you get the desired product in both cases. But where is the difference? The difference is when you sinter them. When you sinter them, then you end up to a situation of this type. So basically, here is the case when the powders have been obtained separately, and this is the curve, the sintering curve, in terms of relative density, of course, when you mix them up. So just if you start looking at this content of afternoon disilicide, you can realize that it is much better if you produce the 2 powders together. Again, because the answer is at the end to keep the audience up, since lunch is almost coming, and then, you know, is necessary to go this way. So we have been really producing very many systems using these 2 technologies, the combination of these 2 technologies. Just to be very, very frank and honest with you, there are no more than 10 labs all over the world that are able to, you know, produce this type of materials. It is not easy, you know, it is very difficult. for many reasons that I don't want to get into, but believe me, it's very difficult. So this is just an overview. But let's go and see a couple of results in terms of characterization. So hardness is very good, as you can see. You get most of the time almost 100% of density. Also fracture toughness is very good. And if you take a look at the binary system highlighted here, then also DTA experiments did show very clearly that you don't lose actually material under oxidation resistance. But the temperatures over here are not that strong. So let's see other characterization. To perform other characterization, we are in contact, strong contact with our friends in Perugia. So this is actually the facility that they have been developing so far. So it's basically an oxyacetylene torch that you are familiar, I'm sure, with. And let's see, and let's go further to see, for example, the samples we have been producing to perform the characterization. So this is actually the flux, the heating flux, and thermocouple with the holes to measure whatever is necessary to highlight. So here, what you can see is actually take a look. I don't have my glasses, so I need to just take a look at these numbers here. And just take a look at the conditions. So we are talking about 450, 150, 1,000, sorry, 2,050, 250 watt per centimeters with this ratio. Very strong oxidation conditions. If you take a look at the delta, the delta weight, it is not appreciable. Under these conditions, for like 120 seconds, 80 seconds, 100 seconds, no problems. The pellet is there and is not affected by such very, very strong conditions. So just take a look at what happened. I'm sorry if I stay here. Oh, thank you very much. Thanks a lot. So just take a look at what's going on when you take a carbon-carbon composite, classical carbon-carbon composite, and you just perform the same, actually, or almost the same, similar ratios. Okay, look at the hole that you get under the same, pretty much the same condition. Of course, the geometry is a little bit different, but you know, it's a very strong test. So in this case, you have an ablation rate of this value, but under such amount of time, basically you get the hole in the sample. While in the other case, I mean, when you talk about UHTC, then no appreciable linear ablation rate can be seen. So I would say this is quite interesting results, So lunch is over there, but a couple of conclusions I think are necessary. First is the fact that the combination of these two technologies, one Russian, say, and another one Japanese, that we brought from these two countries and combined them, are giving very interesting results as far as UHTC ceramics are concerned. Particularly processing time can be shortened very much, and also temperature. I didn't talk earlier about this aspect, but just to give you an idea, if you sinter with the standard technologies at say 1,800, you could do the same at 100, did I say 160? No, 180, you could see, with our technology, you could sinter 1,500 degrees. So Typically, there are from 2 to 300 degrees C different. This is one aspect. The other aspect I would like to emphasize is the one that I put it at the end for the audience. So why is that the SHS powders are very interesting from the sinterability point of view? And there is a specific reason that was somehow demonstrated some time ago by Mishra and his own group, by comparing different technologies to produce the same monophasic zircon diboride. So these are the difference. So basically, this group has been obtained the same monophasic diboride, and then they have been comparing the relative density after sintering. So you see the difference. So you could get higher density with SHS powder. Why? The reason is here. The reason is that because of the rapid heating that you get during the front propagation and the cooling, even also very rapid, then you get defects. Much more defects with respect, actually much more, 10 to the 12, 10 to the 8. Centimeter square per centimeter square, and this is actually the reason why SHS powders are much more easily sinterable. Last consideration is related to the fact that, as you have seen, these materials are really outstanding from the point of view of their own capability to sustain those fluxes under strong oxidation conditions. The reason is here. It was not our own result. Then I put it in the concluding remarks just to let you know that it was clear from a couple of years ago, actually about 10 years ago, that the reason is that there is a formation of borosilicate glass during the oxidation flux that is impacting the sample, that gives you the possibility of reducing the borea evaporation and also acting as an oxygen diffusion barrier, so that the material is able to sustain very well, as you have seen from the results. Thank you very much for your attention.
Speaker, we have time for some question. Yes.
Thank you, Claudio Voto from the Campania Aerospace District. I have a question about the implementation on actual vehicles of this technique. And I was wondering if you, in the mechanical characterization of the material, you are thinking of the point of the problem of impact resistance, the possibility, in other words, that was tied with the brittleness of the material. So you have any activity in mind for implementing the system or toughening the system? Or you have already characterized in terms of absorbed energy? That's one question. And I have another question. The second question goes to the actual configuration. You were indicating a quite important thing with the sintering process, that is the uniformity of the density, and you go to associate that with the actual configuration of the parts that you realize. That makes the tools very complicated, particularly for sintering. So you have any development activity that you are planning for that?
I don't understand the question.
The question is, are you guaranteeing the uniformity of the density with the complex configuration?
Yeah. Well, let me start from the last question. So density is very much uniform within the sample. So when you get, let me go back. When you get, for example, this nozzle here that I've shown earlier, this one here. So this nozzle here has been obtained from a bulk, a cylinder, basically, that was you get a sample, okay, cylindrical shape, then you just machine it, and then you get at the end the nozzles, okay? So the density was homogeneous before and after machining. As far as the complex shapes are concerned, okay, well, you open up a big issue actually. So here the point is, remember that we start from and we work with graphite. With graphite. So basically, it is up to you how to work. Of course, if you want to have a near net shed material, and if you want to have like a mold, complex mold, then you might have difficulties in guaranteeing the homogeneity in terms of relative density. This might be a problem. But if you go the other way around, as we did, so you just produce simple shape, and then you machine them, you are not going to get problem. All right? This is the last question. First question was related to...
Related to the energy absorption to consider the toughness of the material.
Yeah, sure. So basically, I didn't get into this aspect, but if you have seen the last table here, maybe the character was too small and was not possible to read. We have been already working with whiskers and fibers. Silicon carbide whiskers, silicon carbide fibers to go in the direction you were describing. So, unfortunately, I don't have with me the numbers, but fracture toughness is quite good, and maybe some other characterization are needed. I'm not saying that this is the complete picture of the characterization for these materials, but they are very much encouraging for everybody in this field, I guess, and that's something we have been doing already, using fibers to guarantee the characteristics that we want. Thank you.
Any other questions?
From Università. First question is, how difficult it is to machine to obtain a complex shape? And the second one, if you have limitation in size.
Yeah, thank you very much for the talk, which gives me the opportunity to highlight a couple of things. So, difficulty, not really. We have been obtaining this nozzle, and we brought this nozzle. This has been obtained by electro-erosion. Not big problems. It has been done without difficulties. We didn't do it, so we didn't have the direct experience on working on this part or stage of the entire process. But we have not received indications of difficult situations or difficult problems. So, of course, we are talking about, and let me go to the second question. We are talking about of a nozzle that is like 5 centimeters length and 3 centimeters diameter. All right. So it's a small part, which is useful anyway for various applications, but it's a small part. Of course, going back to your question, you cannot use these machines that we have in Cagliari to produce big samples. They are not, the electrical density is not there, okay? You cannot do it with this apparatus. But I'm aware of the possibility of producing materials with whatever dimension using this technology. If you are interested, we have a strong connection with this company, German company, and we could anytime, have a link with them and start seeing if the material can be obtained with much bigger dimensions. Thank you.
So, let's thank our speaker again.
Thank you.